Okay, so let's first write down the governing equations, Navier-Stokes. Okay, so these apply to a restrictive subset of flows, but these are the flows that we're concerned with. In particular, we're focusing on interfacial effects, so we don't have to worry about things like compressibility. So you have a gas, and by changing pressure on it, you can compress it, change its density, but we're going to assume we have constant density. So incompressible. So we're going to assume that the fluid is incompressible. It's homogeneous. That is to say, its fluid properties do not change as a function of position. So we can describe, if that's true, we can describe in terms of two material properties. That being the density and the viscosity. Okay, so the viscosity, there are two different ways to write viscosity. This is the dynamic viscosity. And this is the kinematic viscosity. I always like kinematic viscosity because the units of kinematic viscosity are diffusivity, so it's length squared per time, so it gives an indication of how quickly vorticity or momentum diffuses through a fluid. So for example, if you have a plate and you have a viscous fluid above it, you start pulling it, then the vorticity generated at the lower boundary diffuses into the overlying fluid at a rate prescribed by this diffusivity. So just like if you have a solid from below, then the thermal diffusivity tells you that the rate at which temperature diffuses in. This is a measure of the diffusivity of vorticity or momentum. Okay, so so let's imagine we have this fluid now, homogeneous incompressible fluid, being acted upon by some force. So then we can describe the fluid motion in terms of the velocity field of individual elements, and also we need to know the pressure field within the fluid. Okay, so Navier-Stokes, rho Okay, so really it's like so this is like F equals ma, so it's simply Newtonian mechanics, but it's describing the evolution of an infinitesimal particle of fluid. Okay, so when we write down F equals ma, our mass times acceleration term for an object, this is basically this term here. So this is the inertia of the object. So a fluid parcel will accelerate in response to pressure gradients within the fluid, external forces, and these are viscous stresses. Okay, so which result from the viscosity within the fluid. So they're basically being dragged around by neighboring fluid elements. Okay, and we'll develop intuition about these equations as we proceed. There, of course, this is again restrictive, incompressible, homogeneous Newtonian. So we're assuming a linear stress-strain relation, but this is in some sense the simplest fluid system we can deal with. But we're going to see things, the complications are going to arise through the boundary conditions, and let's see surface tension being the subject of the course. Okay, so notice that. So we have, these are simply properties of the fluid, but it's a set of 4 equations and 4 unknowns. So this is a statement of incompressibility. Okay, so so it's 4 equations because the first equation is a vector equation, so it's really 3. Our unknowns are the 3 components of the velocity field and the pressure. So we have to solve these equations subject to the appropriate boundary conditions. Okay, BC's boundary conditions. All right. So if we have fluid, solid boundary conditions, so we have, for example, a sphere falling through a fluid. It's basically, you have no slip. That is to say, if you have a solid in contact with the fluid has to move with the solid at the boundary. So if we have a surface S, so we have a sphere, say, falling at speed u, then on the surface of the sphere S, the fluid has to be moving with the speed of the sphere. So basically the sphere is going to drag down fluid with it. Okay, another example. If we have convection in a box, say, so just imagine we have, say, a pot on a stove. If we heat it from below, say we have a rigid surface as well. If we have hot and cold, then we're going to drive. If we crank up the temperature high enough, you're going to get some complicated convective flow within the domain, but the velocity on the walls has to be 0. Okay, but this course we're concerned with interfacial effects. So the motions of drops and bubbles, waves, where there are fluid-fluid interfaces. Okay, so imagine we have a drop of oil moving in a drop of water. So we have two phases of fluid now. Let's call the flow inside, denote its variables with carets. So you have then a velocity field and a pressure field within the drop, and then another one outside. And we have a second phase of fluid with those different properties, and we have an interfacial tension at the surface. Let's say this is moving at a speed u. Then we need to know what the boundary conditions are at the surface of the drop. Okay, so we basically then have two fluid domains, and we have to match them together through interfacial boundary conditions at the surface. Similarly, if we have wind blowing over water, we have two different two different domains, air, water. So here, for these interfacial flows, okay, so we have to solve Navier-Stokes. Okay, so these interfacial boundary conditions are going to allow us to match these two solutions together. Okay, and then what makes these difficult, of course, is that these interfaces are generally free to move, right? So you have to apply boundary conditions at boundaries which are free to move. Okay, so the first boundary condition is a simple one. So that basically at an interface, velocity is always continuous. So we can't have discontinuities in velocities, or we'd have discontinuous stresses. Okay, so in either of these two situations, the velocity, the interface is the same, so inside and out. So we have this condition of continuity of continuous velocity, but what about pressure? So we now have to see how the normal and tangential stresses change across an interface. So we've seen already that we've introduced the concept of Laplace pressure. Just heuristically, we know that there's a pressure jump across the surface of a bubble or a drop, which is proportional to the surface tension times the curvature of the interface. So we know that pressure is basically a normal stress. So that's one thing which we have some intuition for. We'll also see that tangential stresses can change across an interface if they're gradients in surface tension. Okay. So we see how the velocity has to be continuous, but our fourth field variable, pressure, we aren't quite sure how that's going to work out. So again, we've seen there's a jump in pressure which goes like sigma over r. So this is in a static state. But in general, so for non-static case, we're going to have to start from first principles. Okay, so that's the subject of the handout. And so the second half of the lecture, you won't need to take notes, but I just want to give you some preliminaries on the stress tensor. So the stress tensor is used in your notes as if you know what it is, and you may not be too familiar with it. And I think it's very important to understand the stress tensors because it's kind of ugly, but it has a nice physical intuition, and then you just realize this is simply a way of keeping track of the stresses acting within a fluid. Okay, so let's recall stress tensor. So this is describing the state of stress within a fluid. Okay, I've also another restriction. So these are I'm only dealing with Newtonian fluids. So Newtonian fluids have there's the stress and strain, which is a question. Stress is sort of is units of force per area. Strain is basically a measure of the local stretching within the fluid. These two are linearly related for Newtonian fluids through the fluid viscosity. So, but these are basically the simplest types of fluids. Non-Newtonian fluids include fluids with sort of like shampoos where there's sort of elastic elements which cause them to stretch, and they actually have a memory. And also you can have rheological fluids, so suspensions like corn powder, and the response depends on how quickly you hit it. But common fluids, for example, water and glycerol and silicon oils are all Newtonian, and that'll be all we'll be concerning ourselves with. The reason I don't like dealing with non-Newtonian fluids is the mathematics is just nasty, and you're usually just trying to back out the constitutive relations. Okay, so a Newtonian fluid the state of stress okay, so state of stress within the fluid. Okay, so our stress tensor denote by T. So double underbar indicating it's a tensor. So it's pressure as a pressure term. And then deviatoric stress tensor, stress component. So this is just the unit. So notice it's basically, so in Cartesian coordinates, it's a 3x3 matrix. So this is a unit matrix. And E here, so this is again the viscosity. Okay, so this is a so-called deviatoric stress. And so you see, first off, before we zoom in and actually get a feel for this, you see that it depends on both the state of strain within the fluid, that is to say, the gradients of the velocity field. Okay, so that's entering, so that's contributing to the state of stress within the fluid through the action of viscosity. Okay, we also see that it depends on the pressure field. So there are two contributors to the state of stress within the fluid. One is the local pressure field, and one is the local velocity gradients. Okay, and those enter through viscosity. If you have an inviscid fluid, these things vanish, and the state of stress is determined entirely by the pressure field. Okay. Okay, I just think it's worth writing out because I certainly have only recently become comfortable with thinking about tensors, but it's, again, simply a means of bookkeeping. So let's actually write it out for a particular case, and then we'll discuss a little bit the physical significance of the stress tensor. So one thing to keep in mind is if you take the divergence of the stress tensor, it actually gives you the force per volume within a fluid. Okay, we'll come to that in a second, but I like to write out. So depending on your coordinate system, if we're imagining Cartesian coordinates, so it's simply going to be then, again, a 3x3 matrix. So each of these 9 components is simply some combination of the pressure field and viscous stresses associated with shear. I just, again, think I'm being pedantic, but I just like to do this. So one thing you'll notice, this thing is symmetric, which is nice. So this is the same as this. So you don't care about the order. The other thing, you see that the pressure only arises on the diagonals. So we're going to say in a moment what each of these components means geometrically. So each one represents the stress, that is the force per area acting on a particular surface in a particular direction. Okay? And then, again, this thing is symmetric. du1, dx3. Then we have mu du2 dx3 plus e3. Yeah, and then we have minus p plus 2 mu du3 dx3. Okay, so again, symmetry tells us this is the same. So this is the same as this. This is the same as this. And this is the same as this. Okay, so so we're going to try and extract as much physics out of this as we can. Just a moment, I just want to, so that the associated, so you can ask, well, what's the state of stress within a fluid? What's the resulting force? So this, you can get the hydrodynamic force per unit volume within a fluid. So we can think of it as force density is simply the divergence of the stress tensor. Okay, so by taking the divergence of a tensor, we're going to get a vector, and this vector is, so we can think of Navier-Stokes now. So rho du dt, so that's the material derivative acting on a fluid element. Do you use this commonly, Andre? You guys?
Yeah.
Do you? So right, so d by dt is d by dt plus u dot grad. So before we wrote du dt in this form, but you can equivalently write it in this form. It's more compact. Okay? So this was our left-hand side. So this is our mass times acceleration term, right? So the mass times acceleration of a fluid parcel is simply then expressed as the hydrodynamic force per unit volume, which is the divergence of T, plus whatever external forces are acting on the system. Okay? So if you expand this, if you take the divergence of this, you get the other two terms in the Navier-Stokes equations, right? So these give the first two. Okay, so these two terms are simply the divergence of the stress tensor. Okay? Okay, so what is, so again, you think of mass times acceleration on a fluid blob. This is the mass times acceleration, so it's going to move in response to applied forces and also internal hydrodynamic forces. Okay, so let's try and come to grips with what this means, and in particular, what each of these elements represents. So this is Tij, so any given component, so this is T11, T12, T13. So it's a force per unit area. So again, it has units of pressure. And you see it must have units of pressure because there's a pressure arising there. And you can always remember mu times a velocity gradient has to have the units of force per unit area. It's the units of pressure. Okay, so acting in the EJ direction, so that's a unit vector on a surface with a face perpendicular to EI. Okay, so let's just draw our Cartesian coordinates here. So imagine we have a box here. Okay, so this is X, Y, Z. So E1 is in the so these are unit vectors in the three principal directions, X, Y, and Z. Okay, so Tij's then, so this is force per unit area acting in a particular direction on the face perpendicular to another. Okay, so we'll do a couple of examples, but things to note. So the normal stresses are going to be these guys, so the 1, 1, 2, 2, 3, 3 components. So that's so we have this cube, so the 1, 1 is going to be acting in the x direction on the face perpendicular to this, so it's basically this one. 2, 2 is here, 3, 3 is here. Okay? So those forces, those normal stresses, or the diagonals, so these involve both pressure and velocity gradients, right? So that makes sense in the sense that when we think of a blob of fluid, we know that there's a normal force acting on it as a result of pressure, right? But it also says that there's going to be some contribution to those normal forces associated with the flow. In particular, you get a sense if you have some stagnation flow hitting a surface, there's going to be some pressure as a result. So, but it depends in general. The normal stresses on a fluid element are going to depend on both pressure and velocity. Okay? But we see the tangential, conversely, the tangential components, which are these guys. So these are basically indicating, for example, if we think of this box, 1, 3. So it's these are going to be forces acting tangent to the surface. Those don't depend on pressure. They only depend on the local velocity shear. Okay. So these tangential stresses, which are the off diagonals, so they involve only velocity gradients, and so the viscous stresses. Okay, third, we've noted already that Tij is symmetric. which ensures that I can never remember whether that's T12 or T21. But it doesn't matter. And in fact, when you derive the stress tensor, you actually this ensures that basically the net torques on an infinitesimal fluid volume balance. Okay. Okay. So if we look now, we can define a stress vector. So if we have a surface with a unit normal n, so if we project T onto n, so that gives us then a vector. So this is a stress vector acting on a surface with normal n. Okay, so that can have any component. It can have a tangential component. It can have a normal component. Okay? And so in some sense, when you're looking at this infinitesimal blob, you're basically projecting out components by dotting with EI, where EI is one of these three unit normals. Okay, so as an example, we have if we have a flow which looks like this, so say we have some shear flow above a rigid boundary. So this is our velocity profile. Let's say this is the x direction, this is the y direction. We can say u in the x direction depends on y linearly. Then you can ask, what's the resulting force per unit area on the lower boundary? Okay. So the force per unit area on lower boundary is going to be Tyx. I should just call that T. Tyx equals mu dux dy. So it's going to, so it depends linearly on the shear, local shear. Okay? So and this is evaluated at the lower boundary. So this is the stress now on the y surface. Let's just say the surface which has a normal parallel to y, and it's the force in the x direction. Okay? And so we see again in general the state of stress within a fluid is going to depend on both the viscous stresses and the pressure. And so we've written out the stress tensor in Cartesian coordinates. In general, you can find its form for arbitrary curvilinear coordinates, so cylindrical coordinates, spherical coordinates. It's a bit more of a mess, but these are in the back of Bachelor. So basically, if you want to find the state, if you know basically, if you can solve Navier-Stokes equations, you can calculate the flow everywhere. So if you have the flow and the pressure field, then you can evaluate the hydrodynamic force acting on an object. Okay, and in general, so for example, flow past. If you're looking at flow past a sphere, if you can actually solve for the flow, then you can calculate the net force acting on the object. And this is a useful thing to have at your fingertips as well. So this is true for a fluid element or for a rigid body. So let's just imagine we have some object moving through a fluid. If you can solve for the velocity field everywhere, then the hydrodynamic force is simply the integral of the normal projection of the stress tensor over the surface. Okay, so basically what you have to do is you have to solve for the flow. Again, T equals minus P I plus 2 mu E. So you have to solve for the state of stretch within the fluid. Then by taking its normal projection and integrating over the surface of the body, you get the hydrodynamic force which acts on it. Okay? Okay, so now I'm going to, now that we have some intuition for the stress tensor, and we've introduced the concept of a stress vector, I'm going to develop the interfacial boundary conditions, but let's take a little break. And from this point, you won't have to take notes. You just have to make small corrections to these notes. Okay? 5-minute break. Any questions? Yep.
I was looking at the experiment with the two bubbles, remember, connected by the... We have the smaller one shrinking, right? And it's natural to think that if you don't consider the pressure variation inside it, it keeps spherical. It stays spherical as it decreases its size. But then it reaches a point where its diameter equals the diameter of the hose. Currently, from the video, the bubble keeps shrinking, right? But it would not be a sphere anymore since then, right? It would evolve into somewhere recurrent.
Right. So yeah, you'd expect. Yeah. So as it sort of disappears into the.
There would be a time where its diameter would be the diameter of the hose. Right?
So go from there to yeah, and then it's.
It becomes flat, right?
Yeah, what's into a flat thing, maybe?
Yeah.
I mean, ideally speaking, right? Ideally speaking.
Yeah, because it will have...
But then so then the pressure is going. The pressure jump is going down, right? Because if it goes to this surface here,
Frankly, it does, right?
then it reaches atmospheric pressure, right? Because then there's no pressure jump if it's completely flat, right?
Maybe it will match the temperature of the...
Was that?
Then
Yeah.
What I'm saying is
But it won't quite get there because the other one there is going to be some jump there, right? So it'll basically go until, I guess, its curvature matches so it's going to be somewhere between this and this, right?
Yeah.
So it's going to basically, that arc there is going to match the curvature of the big bubble over here,
Well, the point then is...
right? So this has to look like that. Yeah. So that's what it'll do. It'll basically go to the point at which that curvature matches this curvature of the big bubble over here, right?
What I found strange is that it reduces its ratio, right?
Yeah.
Up to a point, but then it would have to increase it so it could match it, the other one. So it increases its ratio. How does it do that? Or I figured it's like a blank between these two.
No, but the pressure difference is going down, right? Like it's high here, and then it goes to 0 there. So it basically reaches the intermediate curvature at which it matches.
going down, the pressure then goes down.
Oh, okay.
Right? I had to get water to rehydrate after that bike ride in. I put the shower to good use, though.